The next thing we'll talk about is why does current flow? All of our work so far has been conductors in static equilibrium when the charges are not moving around. So now we'll ask, well, why do they move? So the first thing we'll ask is what happens inside a wire if there is no net external field? So what happens to the charges inside that wire? Well, if we have a little electron inside a wire, it's going to move around because everything is moving around. As our electron moves around, it bounces into things and it bounces off other things. So it hits off atoms or molecules and it just bounces. Overall, that electron doesn't have any net force on it. So overall, it doesn't really go anywhere. You might imagine a bunch of kids in a kindergarten classroom. They bounce around an awful lot, but ultimately they don't go anywhere. Same thing with the electrons because there's nothing pushing them around anywhere. So the electrons have random motion and collision, but no net motion. Okay, what if we do have an electric field? So first let's establish how do we get an electric field. If we take our battery, or if we take our wire and we hook it up to a battery. So let's take our wire, let's put a couple of leads on it, and let's hook those leads up to a battery. Remember, we represent our battery by those two lines. Our battery provides a potential difference across the wire, and we can call that potential difference epsilon, or we can call it delta V. I'll stick with delta V for right now. What happens when we have a potential difference across two ends of a wire is that it makes an electric field in the wire. So let's draw that field. That points from the positive towards the negative. So we get an electric field inside of our wire. Well, let's think about what happens because of that. If there's an electric field inside of our wire, then every electron experiences an electric force. And the electric force, Fe, is equal to the charge on the electron minus the fundamental charge times the electric field. So our little electron right here is going to experience a force to the right. The field is to the left, the charge is negative, so the force is to the right. If there's an electric force to the right, what happens is that that electric force causes motion to the right. Well, as it moves to the right, there's still going to be collisions because the electrons still bump into stuff. So the path of the electron might come forward and right a little bit, then maybe it bounces down, still a little bit to the right, and maybe it goes a lot to the right, then it might actually have a big collision that bumps it left, and then forward and right. Overall, there will always be collisions that send it off path a little bit, but there's a force on it to the right, so ultimately it moves to the right. Just like if the teacher goes to the door, opens up the door and says, kids, it's time to go out onto the playground. All the kids will move towards the door, even though they might bounce around a little bit on their way. So there is going to be net motion. Oh, sorry. That little oops came because my cat just jumped up on my lap. Hang on, I'm going to turn on my camera, see if I can get him to say hello. No, I can't turn it on mid-film. Okay, so I have a kitty on my lap right now. You might hear some purring. Okay, where was I? So there is a net motion of the electrons to the right. And the speed of that motion is what we call the drift. Oh, now he's climbing on the keyboard. Oh my goodness, I'm going to have to put him down. Sorry, kitty. There you go. So there is a net motion of the electrons with a speed that we call the drift velocity. And drift velocity has a symbol of a lowercase v with a subscript of d. Since there's a net motion of the charges or the charge carrier, that means we have current flow. Okay, let's try and get some quantitative relationships here. When we talk about the current flow, we know that current is how the charge moves over time. We can also talk about how the current moves over space, and to do that we define what's called current density. So we'll define current density as the symbol of an uppercase J, and it's how much current flows past the area of the face of the wire. So a circular wire would have area pi r squared. So we can talk about how charge flows over time, or we can talk about how much current passes through an area. Experimentalists see that this current density J is proportional to the size of the electric field. If you increase the field, you get more current flow. If you decrease the field, you get less current flow. So the constant of proportionality we call sigma. So we know that J is I over A, current over area. It's also some constant times the electric field, and that's an observed relationship. So the next question we'd probably ask is, well, what is sigma? How does that come into play? How does the current density depend on the electric field exactly? So let's throw in a couple of relationships that we will talk about more, but probably you remember from a previous physics course. We know from Ohm's law, V equals IR, where R is the resistance, I is the current, and V is the potential. And we also know that potential is the electric field times the distance. And the distance means the distance of the wire. Why don't we just call that L? So there's two expressions for potential. They have to be equal to each other. Let's see, I want to put in that R equals resistance, even though we're going to come to that on the next slide. So IR equals EL, or EL equals I times R. That tells us that I has to be E times L over R. So let's look at our expression for current density. Current density is current over area. Let's put in that current is electric field times L over R. So J is I over A. So E times L over A times R. Remember, we also said that current density was sigma times E. This shows us that sigma must be L over A times R. So that's interesting. The constant of proportionality depends on how long the wire is, what is the area of the wire, of a cross-section of wire, and this thing R, which is the resistance. And we are going to define resistance properly on the next slide, but in the meantime, I'm sure you are a bit familiar with it. So this constant of proportionality, sigma, is what we call conductivity. And conductivity is a property of a material that talks about how easily current can flow. Okay, my writing is getting very tiny here. Those words are how easy current flows. So sigma is a constant of proportionality. It tells how the current density is related to the electric field. It depends on the property of the wire itself, and it's how easily current can flow through the wire. We're going to talk about this more now on the next slide.